Hi. So in the last lecture, we kind of talked about we're branching into a new area of calculus here, where we're going from differential calculus to something quite different. And usually when you do something new like this, there's some new definitions. So there'll be a couple of new important definitions. So let's start right out there. So if I've got a function y equals f of x, it's defined on an interval from a to b, and a partition, so this is something new, and is partitioned like this: x0, x1, up to x sub k, and then all the way up to x sub n, into n subintervals. So before I finish this definition, just see what I've done. I've taken y equals f of x, it's defined on from a to b, that's our domain, and we're taking a to b and dividing it up into n sections, from x0 to x1, from x1 to x2, eventually from xn minus 1 to xn. So there's n subintervals. Each one of those is a subinterval. And a value of x equal to c sub k is determined in each subinterval. So in each one of these n subintervals, let's look at this kth one right here, from xk minus 1 to xk. C sub k is picked in there. It can be picked anywhere in there. Then the summation from k equals 1 to n of f of c sub k delta x sub k is called a Riemann sum. So that's what we're defining, what a Riemann sum is. I probably should say what delta x sub k is. Delta x sub k would be what you get when you subtract x sub k minus x sub k minus 1. It's basically the width of that subinterval. Riemann sums were named after George Bernhard Riemann, who lived in the early 1800s. Actually, he lived in the early to mid 1800s. Unfortunately, he only lived to 39 years old, but is still picked in most top 10 lists of all-time great mathematicians. So in a very short period of time, he did some wonderful things in the field of differential geometry, a lot of things that really solidified some of the ideas of calculus. So, is this something really new? If you remember what we did yesterday when we tried to find the area between the function f of x equals x squared and the x-axis from 0 to 5, that's exactly what we did. We did an RRAM 5, an LRAM 5, and an MRAM 5. The only difference here is that c sub k doesn't have to be at the far right, or at the far left, or at the middle. It can be anywhere in that interval. So what you do is you pick the c sub k, you go up there, and that's going to be f of c sub k. That's this part. And then the delta x sub k is the width. And then you multiply those two together, and what do you get? You get the area of this rectangle. And all this summation is doing is adding up all n of those rectangles. So it's really not doing too much different. What RRAMs and LRAMs and MRAMs are just special cases. This is the more general case of what we did yesterday. So often you work from a general case and then give examples. This time we gave the examples first, and then we're showing the general case. So the biggest difference is, yesterday, all of these delta k's were the same width. They don't have to be the same width. And yesterday, the c sub k's were either picked to the right, to the left, or the midpoint consistently. They don't have to be. So, what is a Riemann sum finding? Yesterday we used those to find the area between the function and the x-axis. And I told you that that's going to turn out to be a really important thing, that you just kind of have to take my word for it, that it's going to be as important as slopes turned out to be on functions. So it was a little bit of a white lie when I said it's finding the area. Because if you look at this closely, f of c sub k doesn't have to be a positive number. If the function were to drop below the x-axis, then it would be negative. And area is the space enclosed in a two-dimensional surface is always positive. Yet, some of these calculations, when we multiply this times this is always going to be positive, this is sometimes negative, and area can't be negative. So, not all math books use this, but some of them do, and I think it's a really nice thing to call what we find with a Riemann sum. And we're going to call it the signed area. And it's actually the signed area that's going to be so important most of the time when we're doing applications. You're going to find that that signed area really has many, many important meanings. So let's just, whenever we do the Riemann sum, when we want to talk about what we're finding, we're going to say we're finding the signed area. And in the next chapter especially, you'll find out what some of those applications are. So, we've got this new thing called a partition. Let's just look at one example of a Riemann sum other than what we did yesterday. So say we had f of x to be the sine of x, and it's defined on the interval from 0 to 2 pi. So we kind of know what that graph looks like. So if we went pi over 2, pi, 3 pi over 2, and 2 pi, say we decide to make our partition, because a Riemann sum depends on how we partition it. Say we go from 0 to pi over 3 to pi over 2 to 2 pi. So we're starting here at 0, and then we're going to pi over 3, and then to pi over 2. So here's my first width, here's my second width, and then I'm going all the way to 2 pi. So that last width is going all the way to 2 pi. And how many rectangles are we going to have? we're going to have 1, 2, 3 rectangles. Now, I also have to tell you what the values of c sub k are. So we're going to pick pi over 6 to be in this first one. So pi over 6 is going to be right here. And then pi over 2 is going to be the next one. And the last one we'll do at 3 pi over 2, between pi over 2 and 2 pi. So right here. So let's take a look what the sine function looks like. We'll put 1 right here. So the sine goes up to here, goes back down, like that. And what we're doing in this first interval from 0 to pi over 3, we're picking pi over 6 to be our c sub k, and we're getting this rectangle right here. And what would that be? Our Riemann sum is now going to be the summation from k equals 1. Now instead of putting n, we're going to put 3 because we have 3 subintervals. And f of c sub k is going to be the sine of c sub k. So that's what our specific Riemann sum here is going to look like. So we have 3 calculations we have to do for our rectangles. Well, the first one, the height is going to be what? It's going to be the sine of pi over 6. The sine of pi over 6 is 1/2. And what's our width? Our width is from 0 to pi over 3, so that's going to be pi over 3. Now, our next rectangle goes from pi over 3 to pi over 2. So it's not very wide. And in that, we're going to pick the sine of pi over 2 to be our height. So that's going to be the next rectangle. So the height is the sine of pi over 2, or 1, and the width is from pi over 3 to pi over 2, which is only pi over 6. So that's going to be our width. Notice that the area here is the same as the signed area because it's positive. But in this last interval, from pi over 2 to 2 pi, that width is much larger. And what's the height? The height is now going to be the sine of 3 pi over 2, which is a -1. So I'm going to go all the way over to there. And now the signed area is going to be negative because the sine of 3 pi over 2 is a -1. So altogether we get pi over 6 plus pi over 6 minus 3 pi over 2, which is 9 pi over 6. So our answer is negative. The signed area, the total signed area, the total value of that Riemann sum is a -7 pi over 6. Like I said, right now you don't know exactly what that's going to mean, but in an application that will have some value, that Riemann sum. So anyway, that's just one example. Now, if we had this definition of a partition. Well, in a partition, here's a new definition. It almost looks like a double absolute value. This is the norm of the partition. And all the norm is the length of the largest subinterval. So it's really pretty easy to see from here, what's the largest of these three subintervals? Well, obviously 3 pi over 2 is the largest. So that would be the norm of this particular partition. So now we're going to get into the last definition I'll give for today, and quite an important one, and that is if f of x is defined on the interval from a to b, then here's the new word, the definite integral and this is how you write it. Looks like a big S kind of stretched out from a to b of f of x dx equals, and it's just like this. Try not to make this too difficult. It looks just like what we just learned. It's the summation from k equals 1 to n of f of c sub k delta x sub k. But then what's different about it, it's the limit as the largest, as the norm of the partition approaches 0. So what we're saying is, it's not just like we did yesterday with the RRAM and the MRAM and the LRAM. Those were Riemann sums. This is an infinite Riemann sum. So this is how most books note it. I personally like to say, instead of the largest partition size approaching 0, the number of partitions, the number of subintervals, I should say, is approaching infinity. So you can kind of see as those partitions, as the number of them are approaching infinity, then the largest partition size is going to approach 0. So what a definite integral really is an infinite Riemann sum. And what does it find? It finds the exact area. But not just regular area, it's signed area between f of x and the x-axis. From x equals a to x equals b. And it's that exact signed area that is our goal. Yes, Riemann sums with n being like 5 rectangles gives us a pretty good approximation, but it's the exact that we're going to look for most of the time. So, this is going to be something, you can see it on my shirt. These integrals you're going to see for the rest of the year, they're really important. We're finding this new signed area. And maybe one other thing before we go to a couple of examples. You'll notice that we have a new operator on the function f of x. So we're going to have this integral sign and a little dx after it. There's always going to be some function in the middle. So this does something to a function, just like our derivatives did something to functions. What was the derivative of x squared? It turned out to be another function, 2x. Well, this is just another operator on the function f of x. The big difference is, what do we get as an answer? We get a number. we get this signed area. We don't get a function of x. We actually get a number that represents something. And there's one other thing, that this x right in here doesn't have any effect on the answer as to what letter we used. In other words, the integral from a to b of f of x dx is the exact same thing as the integral from a to b of f of t dt. The letter you use really doesn't affect anything. You're just dividing this function up into this infinite number of small rectangles, and you get the same number answer in either case. Because of this, in a definite integral, we sometimes call the x a dummy variable. Its mother doesn't like that, but that's what we call it, because it doesn't really affect the answer. It's a variable, it's a letter, but it doesn't really affect the outcome of the answer. So anyway, I think we're ready to look at what definite integrals can do. Well, going over to this other board, one thing they can do is find the area. Well, how can they find the area? Well, we said definite integrals find signed area. So since signed area is so close to area, we probably can use them. But if I want to find the area between this function and the x-axis from 0 to 3, I can't just blindly go 0 to 3 of f of x dx. Because this finds the signed area and we want to find area. It could turn out to be the same thing, but what if this function drops below the x-axis? And that's what we have to do. Before we actually try to find this, we have to see on the x-axis between 0 and 3 what this function looks like. Well, if we factor out that into x times x minus 2, we see if you take that 0 at x equals 0 and x equals 2. And if you take a number less than 0, you get a negative times a negative is a positive. It's 0 at x equals 0, and it's 0 at x equals 2, but between 0 and 2, on the number line, all these values are going to be negative. Like at x equals 1. 1 times negative 1 is negative 1. So we know it's negative in here, and then once you get past x equals 2, it turns out to be positive. So if we really want to find this area in here, what we have to do is split this up into two sections. We're going to take the definite integral from 0 to 2 of f of x dx, but we're going to know that this finds a negative signed area because it's below the x-axis. So what we do is put a minus sign in front of that. Now I'm just turning the signed area into real area. Now from 2 to 3, since this is above the x-axis, we can just go plus the integral from 2 to 3. And if we solve that, then we're going to find the area between this function and the x-axis, and we'll have solved it. So what's the downside? The downside is, are these easy to do? Well, the only way we really have of doing them is to do that infinite Riemann sum, like we did yesterday with the function x squared from 0 to 5. It took quite a bit of time to do that, and that was even a simpler function. That was just x squared and not x squared minus 2x. And now we have to do two of them. So that's the only downside, that these take a long time. Luckily, calculators, even though they aren't very smart, are really fast. and accurate. So what a calculator can do is it can split up the area like from 0 to 2 into 10,000 little rectangles and add them up. And it comes in to be so close to an infinite Riemann sum that with rounding you can get the same answer. So, calculators, I put this on a calculator, and this turned out to be -4/3. Then I was happy that it was negative because I knew it should be negative. But you have to put that negative sign in front of it. And when I did this side, from 2 to 3, it turned out to be 4/3. So it was really easy then to find the answer to this problem. It's 8/3. Now, I don't have to spend a lot of time explaining how you would do that on a calculator. There's a button that you push that automatically comes up with an integral sign, and it gives you a little space there and there to put your a and your b, and then it gives you a space in there to put whatever your function is, and then it goes like that, and you just put an x there, and you hit the button enter, depending on your calculator, and you get an answer. So what the calculator is really doing is it's shading this up. And there's a very little bit of error, but you really don't notice it because they take so many rectangles. Now, and you can also see what would you do without even plugging this into your calculator. What do you know the answer should be? What is the real signed area between this and the x-axis from 0 to 3? Because that might end up being a more important question than what's the area. Well, now we know the answer is going to be 0. Because if I did -4/3 plus 4/3, you would get 0. So you could try that on your calculator, and I would bet you're going to get 0. What is this thing? It's really, I was just showing positive and negative, but it's a parabola. It's going like this, and then it's coming up like this. And it just happens to be that this area here and this area here are both 4/3. So that the area total is 8/3. But keep in mind, the signed area is 0. And that might have some real meaning. Like, for instance, I guess I'm going ahead a little bit. If this happened to be a velocity function of time, what you'd be finding out is, in this 3-minute trip, your total displacement was 0. You went just as much one direction as you did another direction, and that may be what you were trying to find. Okay, so what do we know so far about integrals? They can find area between a function and the x-axis. We did one example. But besides integrals being able to find area, sometimes area can be used to find integrals. Like, say we wanted to find this definite integral right here. Well, I think you can see doing that infinite Riemann sum where we have to get the summation from k equals 1 to n, and your f of x sub k would be 3 minus x sub k, and then your delta x sub k. Remember, when this was just x sub k squared, it took a lot of work for us to find the answer. This has got an absolute value in it, so it's even going to be harder. But if we really just need to find out what this answer is, now that we know that there's this connection between integrals and area, we could just graph this function. What does it look like from 0 to 4? Well, we know at 3, it's equal to 0. And at 0, it's equal to 3. And then at 4, it's equal to 1. So what is the signed area between this function and the x-axis from 0 to 4? Well, with geometry, 3 times 3 is 9, and it's a triangle, so it's 9 halves for an area. And this one is 1 times 1, so this is 1 half. So the total answer to this is going to be 5, because the signed area is going to be the same thing as the area. Well, can we do the same thing on this one? Say I want to find the definite integral from -2 to 2 of this complicated function. And this would even be worse. We'd have the square root of 4 minus x sub k squared in there. In fact, we wouldn't even be able to solve it. Not only would it be harder, but there isn't even any algebra that could actually solve it. So, what's another way we could actually find this? Well, if we graph it, for y equals 4 minus x squared, if you square both sides, you get y squared equals 4 minus x squared, or x squared plus y squared equals 4. What we do is we have a circle that's going from -2 to 2, but we're only looking, if you worked backwards, this would be plus or minus. We're only looking at the top part, right up here. So what this definite integral is doing, it's finding the signed area between here and here, between this function up here and the x-axis. Well, the signed area is going to be the same thing as the area because it's all above the x-axis. So the answer would just be 1/2 pi times the radius squared, because it's a semicircle, and the radius is 2. So you can try it if you want, put that on your calculator, and I bet you get something very close to 2 pi. So I'm trying to get you to understand what this definite integral does, and I'm hoping you're seeing that it really doesn't do much other than make things look cool. In other words, having this, besides the fact you can do it on your calculator, doesn't really make your life any easier. You still have to go through this infinite Riemann sum like we did yesterday. And I've kind of given you a hint that not only do they get harder than the one yesterday, but as soon as you get to very complicated functions, you don't have formulas like you did before to, like the one that Gauss showed us, where you go from k equals 1 to n of k, and it turned out to be n times n plus 1 over 2. Well, you need that to do sum. You need those other two algebraic formulas that I gave you to do like x squared functions and x cubed functions. But as soon as it gets outside of that, we don't have any special formulas that are going to allow us to do this infinite calculation, especially because you have to take the limit as n approaches infinity of that to get the exact answer. So really, this whole integral from a to b, it makes you look really cool when you're writing it down, but it doesn't have any value. It's this infinite Riemann sum that has value. And the downside of it is that it's hard to do, and it's sometimes impossible to do. So that's something we have to get around. But we'll try to work on that tomorrow. By the way, just since we're trying to bring a little history into this, where did that symbol come from? Well, Leibniz. Remember, Gottfried Leibniz and Sir Isaac Newton were the two people who first formulated calculus in the late 1600s. Leibniz was German, and he saw what we're doing is this summation, this infinite summation, and that came from the German word for summation. So that's why that really represents more a summation sign. So let's kind of sum up everything here. What if you had to find this definite integral? Well, certainly, what are the ways we could do it? One way, we could put it on the calculator. But I'm not going to always give you that choice. Your teachers are not always going to give you that choice. So, what's another possibility? The other possibility is you can do it with geometry. Most functions you can't do with geometry. We could do absolute value, we could do straight lines, we can do circles and semicircles, but most functions we can't. But this is just a horizontal line. So you're just going from 1 to 7, and the function is always just 5. So what is the signed area in there? This is 6, this is 5. The answer should turn out to be 30. Now, in general, you're not going to be able to do that. So what's the third way that we've got to find definite integrals? From what they're defined to be the infinite Riemann sum. So we could say the limit as the largest partition size approaches 0, or if you want to think of it as n approaches infinity, and this goes f of c sub k. Well, this function doesn't even have an x in it. So it's just going to be 5 times delta x sub k. Well, with limits, you kind of know we can take a 5, a constant, out front. So I could just move that out front of the limit. And what happens if you add up all these little delta x sub k's? No matter how you divide up from 1 to 7, if you add them all up, I forgot to put in the summation sign from k equals 1 to n. If you add up all these little heights times widths, you can see you're just going to get the total width is just going to be from 1 to 7, or 6. So you get 5 times 6, or 30. So 3 different ways of finding definite integrals. Geometry doesn't work, though, for many functions. Calculators, not going to let you use them that often. Infinite Riemann sums, fun to do, very difficult to do for easy functions, impossible to do for harder functions. So we have a dilemma. So you're just going to have to wait till the next lecture, because I have to think about what we can do to resolve that dilemma. So anyway, have a good rest of your day.